All right, let's get into a really cool piece of NASA history. It's this story about huge ambition, what seemed like a perfect rocket fuel, and then a very cold, very hard dose of engineering reality. This is all about NASA's lost rocket fuel.
I mean, it sounds like a joke, right? How do you park a spaceship? But really think about it for a second. You're in the vacuum of space. There's no air to push against, no tires to turn, no brakes, no friction to slow you down. So how in the world do you steer something as massive as the space shuttle or line it up perfectly to dock with the space station?
The answer, and the whole challenge, really, is figuring out how to master the art of steering in a vacuum.
And the way you do that is with something called an auxiliary propulsion system, or APS. Look, if the main engines are the gas pedal that gets you to orbit, the APS is everything else. It's your power steering, your turn signals, and your brakes, all rolled into one. It's basically this whole network of tiny little rocket thrusters all over the spacecraft that fire in these quick bursts to nudge it, to turn it, to hold it perfectly still. It's absolutely crucial for, well, pretty much everything, from pointing a telescope to docking with the ISS.
Okay, so to power these little thrusters, you obviously need fuel. And back in the early days of the shuttle program, engineers had their sights set on what seemed like the absolute perfect solution, a mix of hydrogen and oxygen. A fuel so clean its only byproduct is water, H2O.
So this is where it gets really interesting, because NASA had this huge choice to make. On one hand, you had the old guard, monomethylhydrazine and nitrogen tetroxide, or MMH/NTO for short. Now, this stuff is reliable. It ignites the second the two chemicals touch, and you can store it at room temperature. But, and this is a big but, it is unbelievably toxic and corrosive. Just nasty, dangerous stuff to handle. On the other hand, you have the new kid on the block, liquid hydrogen and liquid oxygen, H2O. This combo is a performance beast. It's way more powerful, it's non-toxic, and its exhaust is literally just water vapor. So what's the catch? Well, it's cryogenic. It has to be kept insanely cold, which makes it a real pain to handle and to store for long missions.
But just imagine the appeal. You're building a reusable space shuttle, right? So a high-performance fuel that's also non-toxic, a fuel you could literally handle without a hazmat suit, it just seemed like a total no-brainer. The choice felt so obvious. This had to be the future.
And so NASA went all in. They dove headfirst into this dream, planning to build the shuttle's entire maneuvering system around this clean, powerful fuel. The vision was just so grand, a completely reusable spaceship, and this clean, high-performance HO system was a huge part of that. It just fit perfectly with the whole ambitious, forward-thinking spirit of the shuttle program.
But reality, as it so often does in engineering, had some other plans. The big villain in this story was heat. See, even the tiniest bit of heat leaking into the fuel lines would cause that super cold liquid hydrogen and oxygen to instantly flash into a gas. We call it boil-off, and for the thrusters, it was an absolute nightmare.
And you don't have to take my word for it. This quote from a 1991 NASA report really gets to the heart of the problem. That term, two-phase flow, that's the engineering nightmare right there. It means you're trying to shove a mix of liquid and gas through an engine that's only designed for liquid. It's kind of like having big air bubbles in your car's brake lines. You'd get sputtering, unpredictable bursts of power, or maybe nothing at all. The bottom line? The system was fundamentally uncontrollable.
So this left the whole shuttle program facing a very, very cold, hard choice. The dream was crashing head-on into the laws of physics, and someone had to make a decision.
And with all that pressure to build the reliable vehicle, the program managers made the tough call. They pulled the plug. The hydrogen-oxygen APS for the shuttle was officially abandoned. The dream? Well, it was over. The risk was just way too high.
So what did they do instead? They fell back on the old workhorse. They chose the proven, reliable, and yes, highly toxic MMH/NTO propellants. It was a totally pragmatic choice. A classic case of engineering picking reliability over raw performance, especially when you've got astronauts' lives on the line. And that's the system the shuttle flew with for 30 years.
But hang on, the story of this HO fuel doesn't actually end there. See, while it was too tricky for those small maneuvering thrusters, it was still the undisputed king for the big main engines. But NASA had to test those huge engines on the ground, and that created a whole new problem.
Right? How do you do it? Remember, HO doesn't just burst into flame on contact like that toxic stuff. You need a spark, a really reliable one. And the old ways of doing it involve things like fluorine, which is yet another toxic chemical. NASA needed something better, something simpler, and a whole lot safer.
And this is the beautiful, elegant solution they came up with. What you're looking at is the schematic for the hydrogen, oxygen, torch igniter. It's basically a miniature rocket engine in its own right, and its only job is to act as a super reliable, super hot pilot light for the big engines.
And the way it works is just beautifully simple. First, a flow of gaseous oxygen starts. Next, a super rugged spark plug fires up. A split second later, hydrogen gets injected into the mix. And what do you get? Flame on! A perfectly stable 3100 Kelvin flame shoots out, ready to reliably ignite any main engine you point it at.
And here you can see it, going from those clean lines on the engineering drawing to the actual rugged piece of hardware. This simple little device, born out of necessity, became a real unsung hero of rocket engine testing for decades. It's cheap, it's easy to operate, and it is incredibly reliable.
Just how reliable are we talking? Well, get this. Some of these units performed over 400 firings before they even needed to be serviced. 400! That's just an incredible testament to a design that shows simplicity and robustness over anything else.
And that really brings us to the core theme of this whole story, doesn't it? It's this constant tug of war between engineering and ambition.
And here's the big takeaway from all this. The ambitious, high-performance HO maneuvering system, it failed because the engineering just couldn't beat the physics at the time. But the humble, simple little HO torch igniter, it succeeded because it was a perfect, rock-solid solution to a very specific problem. It just reminds you that sometimes the best solution isn't the most powerful or the most advanced. It's the one that just works, reliably, every single time.
So that kind of leaves us with a big question to chew on, doesn't it? As we start planning missions to the moon, to Mars, and even further out, what are we going to value more? Are we going to chase that absolute peak of raw performance, even if it comes with more complexity and more risk? Or does the future of deep space exploration really belong to the spacecraft that are built on rugged, reliable, and simple designs? The story of NASA's lost rocket fuel, well, it suggests there's no easy answer.